So what we say earlier, like if you are talking about the more accuracy of the gases, we will be more modifying the equations, and more modifying mean like it will be getting more and more complex right now. So whatever the approach you are saying, like the equation would be the still inaccurate for the engineering purposes. So we are more like generally, and we are more sometimes we are more interested in the behavior under the vapor dome, and we are more towards the near the vapor dome. So in that cases, we normally use the property tables. Uh, and yes, if you remember, like two independent intensive property would be needed to define the state of the system. So we can say like the thermal equation are of the states now are actually embodied in the tabular form. Let's lay down some of the journal thumb rules for our class or later on the classes. So if you are talking about the if we are talking about the steam, we would be using the tables, the property tables. But if you are talking about the air or most of the gases, we would be talking about the ideal gas law. But if the pressure is too high and we are talking about the near the vapor dome, we would be using compressibility chart and the non-ideal equation of the states. But let me say like for the simplicity of the courses itself, so mostly we are talking about the ideal gas law, not the non-ideal equation of the state. So let's look at the how the tables are organized now. I said like we would be needing two independent intensive property to define the state of the system. So let's the first table we are talking about the saturated, liquid, vapor, water. So we are talking about the saturated state, and we are talking about the liquid vapor water now. So we are talking about the vapor dome itself. If I say like if you are talking about the saturated state, or sorry, it's just itself. So we are talking about the saturated state, and we are talking about liquid and vapor. So we are talking about the this zone now. So we are starting from VF over here, uh, volume VF, and we are ending towards the volume VG. We are talking about the temperature, which would be temperature of the saturation temperature, and we are talking about the pressure, which will be saturation pressure over here. Yes, over here we will be talking about the temperature, which would be less than saturation, and we will be talking about the pressure, which would be greater than the saturation. Over here we would be talking about the temperature, which would be greater than the saturation, and we would be talking about the pressure, which would be less than saturation. So that's what actually we have already divided our vapor dome now. So for the water, most important table is the saturated table, and make let's say for your own benefit, make a thumb rule again. Like whenever the condition are given, so make sure you just first check the saturation steam table. So if you are talking about the two phases mixture, table of this is more important now. And yes, we would be having two tables. One would be saturation temperature table, and one would be saturation pressure table. As we in both cases, we might be given like the temperature, and we might be given in terms of pressure as well. So for the saturation state, as we talk about these two independent property earlier as well. So if I'm talking about the temperature, if I want to find the temperature, I can find if by volume and the quality. If I want to find the pressure, I can find by using volume and quality. If I'm talking about the volume, then either of them, like temperature or pressure, and also the quality now. So quality would play a major role in the vapor gas mixture zone now. So we said like we are talking about the temperature table. So the first column would be given in a temperature, and obviously the other one would be there. Like the other columns are pressure column, and I said like there would be volume VF, there would be volume VG. We are still a little bit ignoring the other one, and we will be talking about like enthalpy and entropy in the next few lectures. And yes, Vg minus Vf we have already talked about it, but Vg minus Vf would be equal to Vfg. So if we have been given a temperature, for example, temperature at 15 degrees centigrade, and that is actually our saturation temperature. So for that saturation temperature, the concept is, for that saturation temperature, there would be saturation pressure, and that for that saturation temperature, there would be saturation liquid volume, and there would be saturation gas volume. So let's move forward like over here. So for if I've been given a temperature 15 degrees centigrade, for that temperature, there would be saturation pressure, there would be saturation liquid volume, and there would be saturation uh, vapor volume or gas volume, and obviously the difference between them. Let's say for another temperature. So for that temperature, let's say if I'm saying like I've got a temperature, so there would be saturation pressure over here, there would be saturation liquid volume, and there would be saturation gas volume as well. So talking about this one, let's say let's rewind some of our basic concept in our last lecture. So I am drawing TV diagram as we are talking about the temperature and temperature table over here. T and V diagram. So let's say if I'm saying like if I've been given a temperature over here, so for that temperature, let's say 15 degrees centigrade. Sorry, that's automatic line drawing. So for 15 degrees centigrade, so that for 15 degrees centigrade, I have been given a pressure which is 1.705, let's say, and that is in a kilopascal. And that for that 15 degrees centigrade, I've been given a volume which would be Vf, which is somewhere 0.001001. For that volume again, 15 degrees centigrade, I've been given a volume which would be Vg, and obviously Vg minus Vf would be equal to Vfg over here. So that is our case number one, let's say. Now let's talk about like at another temperature. So that means like another temperature which is greater than 15 degrees centigrade. And let me say like I just pointed out, and that is 40 degrees centigrade. 40 degrees centigrade over here. So if I'm talking about the 40 degrees centigrade, so you can imagine like our pressure would be now greater than, so if I'm increasing the temperature, I'm increasing the pressure as well. So now our pressure is 7.384. Now let's check the volume Vf. So the graph is tilted a little bit forward now. So that means like our Vf would be now greater than at 15 degrees centigrade now. So previously it was 0.0010001. Now it is a little bit increased from 0.0 increased to 0.001008 now. But let's check this one now over here. So our Vg over here was 77.925. Now our Vg is decreased to 19.5229. That's what actually in a previous lecture we said, like if I increasing the temperature, although there would be the pressure would be increased as well, but the difference between Vg and Vf, that would be decreasing. So that's the difference between them, and that is decreasing. So this is a little bit of the saturation, liquid vapor, water temperature table now. Similarly, it will be for the pressure as well. But before going towards the that one, so that's what actually I will a little bit explain over here in my example. Now we define Vfg as approximately equal to Vg minus Vf. It is what we call it as the volume of evaporation. Vfg is volume of evaporation. Recall that quality is the mass of the vapor divided by the total mass. V itself, total volume, is equal to, if I'm talking about the vapor and liquid from the our experiment of a piston and cylinder having boiling the water. So that means like we were having a volume, and that volume was a volume of a liquid and volume of a vapor. I'm talking about the total volume. And if I'm talking about the mass itself, so mass would be mass of the liquid and mass of the vapor. So the specific volume, if you remember, specific volume is equal to total volume divided by the mass. And if I'm talking about the specific volume VF, let's say that will be volume of a liquid with the mass of the liquid. And if I'm talking about the specific volume Vg, so that will be volume of a gas divided by the total volume of the gas divided by the mass of the gas. Just abbreviating them so you can imagine. So that means like specific volume now itself, specific total volume, sorry, itself, this one would be equal to mf mass of the liquid multiplied by the volume of the liquid, and the total volume of the gas would be mass of the gas multiplied by the total specific volume of the gas. So it will be something like this. So volume, total volume in terms of specific would be something like this. So rewriting it and dividing it with the mass somewhere here. So the equation would be something like this. So V is equal to now mass of the liquid divided by m, and Vf into mass of the vapor divided by m into Vg. Remember, like for mass, total mass is equal to mass of the liquid plus mass of the gas. So that means like mass of the liquid itself would be equal to total minus mg over here. So that means like m minus mass of the vapor. So like this. So now we already defined mass of the vapor divided by m is as a quality itself. So that means that would be 1 minus x, and that would be x over here. So rewriting it, so we would be having v is equal to vf plus x vg minus vf, or in other terms v is equal to vf plus x vfg. So that this formula we will be using very much in our next lectures. And now we can define quality in terms of volume now as well. As I said, like similarly for the saturated liquid vapor pressure table, so we would be having now the pressure at one side, and if I let's say if I the pressure is defined, so the temperature would be also defined, Vf would be defined, Vg would be defined, and so on the Vfg. So if I'm increasing the pressure, so on and so forth, that would be there. Uh, just check the table. The table pressure, initial pressure is 0.613 kilopascal, and the final pressure is 22.89 megapascal. So just checking, this was our temperature, the temperature at triple point, and this was our pressure this was a pressure at triple point, and this was our pressure at the critical point. So that means like our table start from the triple point, sorry for that, it can be just TP. So our pressure start from the triple point and end at the critical point. Similarly for the temperature, if you can say like this is our triple point temperature for the water itself, and this is our critical point temperature of the water. So the temperature start at triple point, the table start at triple point, and the table ends at critical point. So that's our critical point condition. And remember, I said like when we reach at critical point, there is no difference between Vf and Vg. So that means like Vf is equal to Vg is equal to critical point temperature. Moving towards the superheated condition. Now in a superheated condition, the temperature and the pressure are independent. So at a column side we would be having a temperature, and at a let's say row side we would be having a pressure. For different table we will be having different one. So we can talk about now the volume. So if we have been given the temperature, as the temperature and pressure are independent now, so we will be having a temperature, we would be having a pressure given, and for that pressure and temperature we would need to find out the volume or internal energy or enthalpy or the entropy, which we will be talking about in our next few lectures now. So this is our supercritical uh, uh, supercritical water table now. Similarly, it will be for the compressed table. So for the compressed table, again we would inside the compressed region, temperature and pressure are independent on each other. So that means like we would be given the the temperature as well. We would be given the pressure as well, and we will be talking about this one. We can have a solid vapor diagram as well. We can have a table for the other material as well. But in our course, we would not be talking about the solid vapor diagram. Yes, in our next semester, you would be learning some metallurgy and material side. So in material and metallurgy side, you can actually talk about the solid vapor diagrams and the table for the solid and vapor. Um, our courses we can talk about the different material as well, material of for example material of sorry the substance which is R41 10A or R314, carbon dioxide tables, right, ammonia tables. But yes, again I'm saying like I am restricting myself to only water, and yes, we would be talking about the ammonia, we would be talking about R314, 134 in our refrigeration and air conditioning courses. So we would be restricting ourselves to either the ideal gas and the steam or the water. Thank you very much. Like if you have got any question about this lecture, you can post in the classroom.